In the previous video, we have seen the motivation for receiver diversity and how we can effectively combine the signal when we have multiple antennas at the transmitter. And there we have seen that if we have a signal coming at first branch, let's say in this form, and we have another signal that is coming and if we have a level crossing rate, let's say this is the LCR or gamma TH, and then if we combine these two signals, it will select the best of the two branches. And it can be seen that it hardly goes below the outage threshold, or it hardly goes below the gamma TH. Whereas in case when you consider the single branch, let's say blue one, there are the chances when the signal goes below the threshold for both the branches. So this kind of combining where we select the best signal from the branches, from different branches, this is known as selection combining. Or we can also say that if we have a transmitter and we have multiple antennas at the receiver, as if we have a switch that is present at the receiver which select the best from all the branches that we have at the receiver. So the selection combining selects the best out of all the branches, and it reduces the dynamic range of the received signal. And what we mean by this is that, let's say if this was the level in which the signal at blue antenna was fluctuating, and now for the blue one, let's say this was the range where it touched the minimum level, and this was the higher. So when we talk about the combined signal, the signal variation is now reduced compared to the signal what we have at individual antenna elements. So as a result, there is less fluctuations in the combined signal. So this can also be seen as if this is the signal fluctuations for the first antenna, and if this is the signal fluctuations at second antenna. But when we combine the signal that we are getting at both the antennas, what eventually the signal we will have, it will have very less fluctuations in it. So the dynamic range will be reduced for the receiver. So now when we have multiple antennas at the receiver, let's say we have m number of antennas, and there will be multiple channel coefficients between each of the links, and we will receive multiple copies of the same signal S that is sent from the transmitter at the receiver. And so we can write the received signal equation as yi is equal to yi, that means the signal received at the ith branch, hi, the channel coefficient corresponding to the ith branch, s plus noise corresponding to each of the branch. And as a result of selection combining, let's say we have this I star is the branch that provide us with the best SNR from all the branches that we have. Then the received signal can be written as yi star is equal to hi star s plus wi star. And I star is equal to the maximum branch is equal to the branch that is the ith index, the branch that provide us with the maximum value of the received signal strength. And also each branch will have its corresponding SNR, which is given by mod hi square gamma, where gamma is PS by sigma w square, where PS is the power corresponding to the signal, and this is the power corresponding to the noise. And then also H is relay. So mean of Hi will be equal to 0 and the variance of Hi is 1. So when H is relay, H square will be exponential. So the PDF of SNR is given in this fashion, which is exponentially distributed. Here, gamma bar is the average received signal strength, which is in turn equals to gamma, because gamma is equal to expectation of Hi into PS by sigma W square, where this value is equal to 1. So this will be equal to this. So we can just change the index to gamma bar. So now outage probability that a signal corresponding to the each branch is less than the gamma TH is given by this particular form, where we get the outage probability as 1 minus exponential of minus gamma TH upon gamma bar. And this is the outage probability that each of the branch will have a signal less than the gamma TH. And from here, we can also compute the fade margin, how much fade margin is required if we say that we need to have a desired outage probability. And this is given by 10 log 10 gamma bar minus 10 log 10 gamma TH. For example, if we have, if there is a requirement that we need to maintain a certain outage probability, and this is the gamma TH, then this should be the gamma bar, and this difference will tell us what is the fade margin, where this will be in dB decibels. Now the outage probability, this was for the first one branch, single branch, outage probability corresponding to the single branch. Now if we want to compute the outage probability for this selection combining technique, where all the M antennas are independent and the signal is received simultaneously, because this is the case where we have said that all the antennas at the receivers, they are uncorrelated. And also if there is some correlation between the antenna elements, then also we can design some other kinds of combining techniques and we can utilize in some or certain way. So the antennas are uncorrelated and they are independent. So the probability that the signal is less than the gamma TH will be equal to the all the branches. If the combined signal is less than gamma TH, indicates that all the branches, the SNR corresponding to all the branches should be less than gamma TH. So this is given by this form, where M is the number of antennas at the receiver. And the probability that SNR is less than gamma is given by this particular way. And this is the CDF. Then by taking the differentiation, we can compute the probability density function of the selection combining. And then we can also compute the mean SNR in this case. And if we compute the mean SNR of selection combinings takes the form of this. Gamma bar summation over K 1 by K. And when K is equal to M, we can have this form. And you can see that whatever be the value of M, this value will always be greater than 1. So thus it can be easily observed that there is always a certain gain that we will achieve when we are using selection combining, and it will always be greater than gamma bar. We are not saying that this will be the optimal, but we are just saying that we can achieve certain kind of gain when we have multiple antennas at the receiver and we are using selection combining. That means we are selecting the signal that is best corresponding to each of the branch. We just select the best branch.